authorities. And the CA, the certificate authority, authorizes the certificates with cryptographic signatures. And your computer has a big list of CAs that it trusts, like VeriSign, GoDaddy, and Thought. And when a client receives a certificate, it goes through its database of the ones that it recognizes, CAs, and checking if the certificate is signed by any of those. After that, it can decide if it trusts the website or not. Except, there may still be something missing. So imagine that Bob's IT person gets a certificate for bobsburgers.com, and this is signed by a trusted CA, so it's totally legitimate. This IT person goes to Starbucks and sets up a spoof server that redirects all of gmail.com traffic to their laptop. They use the bobsburgers.com certificate for the spoof gmail.com site. And your client will say, sure, it's signed by my CA bundle because bobsburgers.com certificate is actually, in fact, signed. But oops. So fortunately, we have hostname checking to the rescue. Clients can check that the hostname on the certificate they receive is the same as that they requested. This is an important line of defense against MITM attacks. But there are other checks involved in invalidating a TLS certificate. For example, is the certificate past the expiration date? If the certificate was compromised, it can also be revoked. But revocation is a different kind of mess. I won't go into it right now. Let's talk about encryption, but not really. So encryption, I used to think it's magic and it's a lot of math and it's not something that is easy. But that's not the point here that I'm trying to say by saying it's magic. What I'm saying is to build secure software, we don't really need to understand all of the crypto math that is involved in it. And for the purpose of this talk, I'm going to treat it as a black box and still talk about how we can go about securing things on the internet. But in general, encryption is the encryption math is a little difficult, but it's not that bad. If you look at it, it's kind of interesting. So TLS, or transport layer security, I want to talk about how it works or how it's supposed to work. And to explain this, let's look at a session negotiation. It's a network protocol, right? So there's a client and a server involved. The first and the most important thing in the TLS protocol is the handshake. So the client tries to establish a connection by sending the server a client hello message. And then a lot of stuff follows. I haven't put this really weird looking block diagram in my slide to actually go through it line by line. But I will tell you that it's a lot of things happen. Client hello is followed by a server hello, then the client and the server exchange information, keys, a few secrets, and the other thing they need to establish a connection. And then during this process, a lot of decisions are made. And once those decisions are made, the switch of encryption is flipped, and in theory, everything is secure now. Also, when we're talking about TLS, the software that deals with TLS can be classified extremely broadly, probably, into the software that implements TLS and the software that actually uses TLS. First, let's take a look at some of the TLS implementations that are out there. OpenSSL, probably the most widely used one. There's Boring SSL that Google tried to do things with. I don't think they recommend using it yet, so check with the documentation before you think about using it. There's secure transport, there's NSS, channel, there's GNU TLS, and a lot more. But these implementations have a lot of flaws, both in the way that they're implemented and in the APIs that they expose. But there's an interesting commonality in all of the popular implementations of TLS. All of them are written in C or C++. And they've all had bugs caused by memory and safety. Some of those bugs were really, really big. I'm sure many of you remember Heartbleed if you deal with anything that used OpenSSL in 2014. So Heartbleed was a simple lack of bounds check that allowed attackers to retrieve random data from the RAM. It was not a crypto flaw. It was just a classic don't write network code in C moment. A lot of the flaws are also just plain logic errors in the implementation. Multiple TLS implementations have had bugs accepting any certificates as valid if it's signed by a trusted non-certificate authority certificate. So that's like, for example, bobsburgers.com could sign a rogue certificate for gmail.com, and that would be accepted, even if that certificate is not a certificate authority certificate. And the thing in the background, it's not just some random background tile. It's an actual documented way to write a simple TLS client in OpenSSL. So this is not just a crappy verbose API, it's an unopinionated API, which means that you have to use your own settings. Remember the many, many decisions that I showed on a slide initially in this talk. Forcing application developers to make those decisions themselves is a bad idea. First of all, it allows them to make bad decisions. And then it prevents applications from being easily migrated to better settings as and when they become available. So all of this could be so much better. And well, there aren't just implementation flaws, there are some protocol flaws as well. SSL and TLS have a rocky history with backwards compatibility. There have been a ton of downgrade attacks. These allow attackers, usually man-in-the-middle attacks, to prevent a secure connection from being established, which further allows them to take advantage of the flaws in the less secure session that they've created. Next, I'm gonna look at some problems with HTTPS. Even though HTTPS is just HTTP on TLS, there are a lot of interesting, unique attack vectors involved here. There are not problems with the authentication or the cryptography. They're rather attacks based on subtle browser behavior. For example, cookie stealing is like a really interesting one. The user connects to a secure HTTP website that stores a cookie on their system. So far, so good. The attacker cannot attack this encrypted traffic to the target website, but they wait for you to submit an unencrypted HTTP request to any other website. And then the attacker steps in and responds with a redirect to the target domain and on port 80. Now, because any site can issue a redirection to any other website, your browser happily follows. And this results in a plain text connection to the target website, which includes all non-secure cookies in your browser's possession at that point. This can be mitigated by setting a secure flag on your cookies, but many developers forget to do that. This is a part of all the, I have been emphasizing why it's a bad idea to allow application developers to make decisions about security on their own. So this exemplifies how tricky securing HTTP is, and it's an extremely complicated combination of factors. And even when the cookies, even when you set the secure flag on your cookies, there is still the possibility of cookie injection. This uses a similar technique. Non-encryption breaking, man in the middle can redirect to the target domain on port 80 and send a set cookie header to override the arbitrary cookies for that site. So your secure cookies are not resistant to tampering either. So also in a lot of cases, the user can be considered a security flaw because users do insecure things, right? For example, clicking through certificate warnings when you tell them that their website, the website they're trying to access is not really secure. But I don't think it's really the user's fault. We don't prevent them from connecting to sites with invalid certificates. We train them to click through warnings by just having so many of them. Moving on to software that uses TLS, we can recall our example from the beginning. Even though this supported TLS, it was used incorrectly, causing huge security holes. So I don't, like, it's easy to blame urlib2. It's like, we can say that it's bad, but not really. I think that it's more of a failing of the industry. If easy, opinionated secure TLS APIs existed, we wouldn't have had this problem in the first place. So this is like the usability problem with browsers, but for developers. Fortunately, the requests library exists. So if this is the same code that I showed you on the first slide, written using requests. With this, you will receive an error if the website has a bad certificate. But it is sad that urlib2, which almost every new Python programmer will use, is horribly insecure. Everyone in the know uses requests, though, because it's secure. Well, I mean, they use it because it's easier to use, but it's also secure. Well, I know I'm being really negative with this talk. I've showed you all of the ways that the existing libraries have flaws in them, but on a positive note, things are getting better. People are beginning to care, which is a great thing. And OpenSSL itself is getting more attention. So, well, the more we know about the flaws, the more it makes it easier to improve. New alternatives are showing up. There's boring SSL, there's libSSL. There are a lot more, and which means that there's hope. And things could still be better, though. Most of these libraries are still implemented in memory and safe languages. PyCA here is a group of people who call themselves Python Crypto Authority. They are trying to write a library called Cryptography, which is a Python project that aims to have opinionated APIs while still exposing low-level primitives when required, so that if by default you'll have a secure application, but if you want to go in and make changes, you're still allowed to do that. This hides the complexity and at the same time makes it easier for someone who doesn't want to make all those decisions on their own. There's also PyCA's TLS, which was something that I started working on in Stripe's open source retreat last year, but I haven't quite had the time to work on it further. But if any of you awesome people are interested and want to contribute, please, please, please do so, and I will make more time to ensure that your efforts don't go waste. So this is my favorite part of the talk. What can we do? First, we can use all the tools that are available on the internet to make sure to check if our applications, if everything that we write is secure or not. It's not possible to be 100% confident about this, but it helps to know that there are tools out there. SSL Labs has this thing called SSL test. It's really good. There's Hinix page about configuring TLS, which tells you what are by default, what are the secure options that you can use. And he keeps it maintained on a regular basis, so it's always updated, almost always updated. There's also, there was some talk about working on a list of servers with bad certificates so that you could test your clients against them and check if you detect the bad certificates. There is also, this book called Bulletproof SSL and TLS is, I think, the book that taught me almost everything I know today about SSL and TLS. It's a really good book that starts from the basics and teaches you a lot of detailed things about security and the internet. There's this book called The Tangled Web. I haven't seen a single person who's read like more than one chapter of the book and still remained happy about the state of security on the internet. It makes you feel like everything is broken and there's no hope, but it's a really good book and I really like it. There's LVH wrote this book called Crypto 101. I think it's available for free on the internet, and it's a really good book that talks about the basics of cryptography for developers who do not need to understand all of the encrypted math. It starts from level 0, so that's also a good book. And finally, I know the state of things seems scary. The whole subject of cryptography, security seems really, really scary. But I would say that please be brave, learn about these, and contribute. Help us out on the cryptography project. There's a channel called Cryptography Dev on IRC Freenode. Join in, ask questions. We're here to help. And thank you. I think we have a few minutes for questions. Yes? Sorry? I don't know if there's a name for it. I think it's just it's the inability of URL open to detect bad certificates or not do certificate validation by default. But I might be mistaken. I can look it up for you. Yeah. Anyone else? No? Okay, very good then. Thank you for coming and attending my talk.